Okay, welcome everyone to the Wednesday morning session of FPSAC 2023 in sunny Davis, California. A reminder that this afternoon will be the free afternoon. There will be more information provided about the various excursions, I believe, by Ashley a little later. But for now, I am very pleased to announce that the plenary talk this morning will be given by Melody Chan. She'll tell us about graph complexes and moduli spaces in tropical geometry. So without further ado, Melody, please take it away.
Thanks, Sam, for the introduction. Thank you. It's a great pleasure to be here. I want to tell you about a story of graph complexes as introduced by Kontsevich in the 90s. These are a certain rational chain complex generated by oriented graphs, whose differential is some kind of sum over one-edge contractions. So the definition is purely combinatorial, but these objects have deep connections to geometry in multiple ways. And we discovered one such way. This is in joint work with Soren Galatius and Sam Payne. I think that these ideas, though in some sense purely combinatorial, are a little bit outside of center with respect to most combinatorial audiences. And I think that the way I can give the most accessible talk is to give you precise definitions, letting you explore them alongside me. So the plan for the talk will be to give you a precise definition of graph complexes. And in the third part of the talk, I'll explain the connection we made to moduli spaces in tropical and algebraic geometry. And in the second part of the talk, I'll connect the two using a combinatorial topology construction that I also wish to define precisely for you. So let me start. Graph complexes. I'll denote this GC for graph complex due to Kontsevich in papers in the 90s. And I'll give you a precise definition. As I said, this will be a rational chain complex generated by graphs. So to start with, it's a graded Q vector space. As a Q vector space, it has generators as follows. Pairs G comma eta, where G is a graph, always connected. And when I say graph, I mean for the purists a multigraph. Loops and parallel edges are allowed. And I'll impose the condition that the valence, or degree, graph theoretic degree, of a vertex is at least 3 for all vertices of G.
Are the graphs labeled?
Are they what?
Labeled.
Labeled. No. The orientation data will be this eta, which in words, I'll write it first, is a total ordering on the edge set, but only up to the action of even permutations. So it's one bit of data, and in symbols, eta is an element of the top exterior power of the free Z module generated by the edges. This is isomorphic to Z, it's rank 1, and I take a unit. Sorry, this is a unit. So in words, it is a total ordering on the edges, but only up to the action of even permutations. These generators are put into degree, the degree of G comma eta, by definition, is the number of edges minus twice the genus of the graph, where G is, just to recall, the genus of the graph. It's the first Betti number of the graph. In other words, the number of edges minus the number of vertices plus 1. This is a graded vector space so far. Yes?
Do we identify isomorphic graphs?
I'm about to give you the relations on the generators. So, this is a list of generators. Now I impose relations, which take care of what David said. There will be at most one generator, sort of after imposing relations, per isomorphism class. So the first relation is that G minus eta is identified with minus G eta. Minus eta denotes the other orientation. So anything obtained from eta by composing with an odd permutation, or in the symbols, literally minus eta. So that's relation A. And more generally, relation B is if you have an isomorphism phi of graphs, say from G to G prime, then we impose that G comma eta for any edge ordering eta is identified with G prime comma the edge ordering obtained from eta by composing with the isomorphism, which I'll write phi sub lower star, if that's fine. So from these relations, you can see that, in fact, there's at most one basis element for every isomorphism class of graphs. I definitely owe you an example, but let me just quickly finish the definition entirely of GC. See, we now have a graded vector space, and now I need to tell you a differential. So the differential is defined as a signed sum of one-edge contractions. So let me write eta as the wedge of E naught through E sub p. This is my total ordering on the edge set. And now the differential is defined as the signed sum over all one-edge contractions of G with the induced orientation obtained by omitting edge EI in turn. This edge contraction, let's agree right now that it is to be interpreted as 0 if EI was a loop edge. Whereas if EI is not a loop, then contracting an edge preserves the first Betti number, the genus of the graph, and decreases the number of edges by 1, evidently, so that this differential really is a differential in degree -1. And that's the full definition of Koncevich's graph complex. He actually defined a family of graph complexes. In fact, that definition can be extended in work of Conant and Voetman to a graph complex, one for every cyclic operad. And if you're into that, this is the commutative graph complex, corresponding to the commutative cyclic operad. The main problem, and I write this as a problem not to say that we should all dive in to study it, it is hard, but it is sort of foundational, is to study the homology of this graph complex, by which I mean, as usual, the kernel of the differential mod the image of the differential. This is a hard problem with multiple connections in, as far as I can tell, different directions to various areas of geometry. So now I owe you some examples. Let me start with an example that is something that's actually zeroed out in the graph complex, so maybe something like this. So I need to tell you a pair consisting of a graph G, here it is, and a total ordering on the edges. So if it's OK, I'll write numbers on the edges to indicate the total ordering. And this generator, by relation A, is equal to negative of G minus eta, where minus eta is any edge ordering obtained by composing with an odd permutation. So for example, I could swap the labels 1 and 2. But by relation B, this, noting that there's no requirement that G and G prime be literally distinct graphs, we can take the automorphism of the graph. This is different than A. The automorphism of the graph that switches these two edges. And then the edge ordering comes along with the automorphism. So we actually restore, in this way, the original edge ordering. So we conclude that this generator is 0, since it's equal to its negative, and it's an element of a vector space in characteristic not 2. Is that example clear? So more generally, what we've shown here is that a graph G with any edge ordering eta is 0 in the graph complex GC if G has non-alternating automorphisms, by which I mean the graph has some automorphism that acts by an odd permutation on the set of edges. I think that the definition of an alternating graph, which let's make it right now, it's a graph whose automorphism group acts via alternating permutations on the edge set, is an interesting definition that is not standard in graph theory. So for example, it's an open problem to count alternating graphs. For example, there are a finite number for each genus with the valency conditions imposed on the first board. This is an interesting condition, e.g. as it relates to the graph complex. So far we've seen only an example that's trivial, that's 0. Let me show you the smallest non-trivial example. And this is already deep. So though these definitions are combinatorial, they have a little bit of a different feel than some of my favorite combinatorial problems in which you can just jump in and try stuff. It's a little delicate to actually find non-zero homology classes. In fact, it's quite hard in general. So here's something I claim is highly non-trivial. It's the graph K4 with any edge ordering you want. And let's, as practice, compute the differential of K4. To do that, you have to contract each edge in turn. But you notice that K4 is a graph that is covered by triangles, meaning that every edge is in a triangle. And if you contract an edge of a triangle, you obtain parallel edges. So the resulting graph is 0 in the graph complex. So the differential is 0. In other words, K4, and indeed any graph covered by triangles, is 0. So its class, it is a homology class, in this case in degree 0, since the number of edges is equal to twice the genus. So again, what I mean here is that like how do you give a homology class? You give a representative of it, something whose differential is 0. Now I need to argue whether or not this is trivial, whether this is 0 as a homology class. In other words, is this the image of something under D? I claim that it isn't, and here it's a combinatorial argument. If it were, you would have to involve graphs that were obtained from K4 by edge uncontraction. But uncontracting at a valence 3 vertex produces a valence less than 3 vertex. And these don't appear. So actually, this is in top degree and is therefore non-zero as a homology class for the simplest reason possible. That's our first non-trivial computation. And I think that this is deep. This is related to a number of different concepts. For example, a certain top-weight cohomology class of the moduli space M3. Let's come back to combinatorics. We would love to generalize this non-zero homology class. What are ways to generalize the graph K4? Kn, okay, great. So one way, let's see. Let's consider for each k the complete graph k sub little k. This complete graph is certainly still covered by triangles, so it represents a homology class in whatever degree, twice the number of edges minus twice the genus, whatever that is. And I claim, this is an exercise, that this is a non-zero in the sense of the middle board. Sorry, the graph itself, kk, is non-zero as an element of GC if and only if k is even, like for example, k equals 4. So you can ask whether these homology classes are 0 or not in the graph complex. And I have a very unsatisfying answer for you. They are 0, meaning that they're the image of something under the boundary map, but I have no idea how to write down that something. And I think no one does. This is open in the sense of finding a combinatorial proof of this triviality of the complete graph homology classes. The reason I know this to be true is that it's a deep theorem of Wilvacher that actually the homology of graph complexes vanishes in every negative degree. And you can check that this degree just happens to be negative when k is greater than 4. Sorry, so this is 0. This is for k. Not that example, so k greater than 4. This is a deep theorem of Wilvacher, which is proved using quantum algebra techniques, which frankly I cannot understand. We have a different proof that uses homological vanishing of moduli spaces, old result due to Harrer, using the connections that I'm sort of talking about in this talk, albeit implicitly. So both of these proofs are, as far as I can tell, completely different, and neither of them is combinatorial. I think it'd be interesting and fun, and probably hard, but I haven't tried it, to find a linear combination of graphs whose boundary is equal to the complete graph. H less than 0, H negative degrees, yeah. Yeah, thanks. So what's another way to generalize K4? It's, oh yeah. I can't do that. I'm like working with graphs. Okay, I'm going to go with what I had planned, which is the wheel graph. So K4 is also known as wheel 3. So in general, WG is the wheel graph on 2G edges. It's obtained by taking a cycle of length cycle of length G, and adding an apex vertex adjacent to all. You can check that WG is alternating in the sense we discussed, if and only if G is odd. Moreover, WG is certainly covered by triangles. You can see it. So it represents a homology class. I'll suppress the eta since it doesn't matter. It's in degree 0 since the number of edges is twice the genus. And it is a deep fact. It's probably the sort of scariest thing I know about graphs, that these wheels represent non-zero homology classes for G at least 3 odd. This fact is due to Rossi-Wilvacher, later Wilvacher, with a different sort of related, different proof in forthcoming work of Brown-Schnetz. And the reason that these are scary results is that they involve integration of forms over certain domains associated to the graph. And I know of no non-transcendental proof. You can work things out by hand for small cases. For G equals 3, we did that. For G equals 5 is an exercise. For G equals 7, there's actually a computational paper by 3 physicists that just writes out this giant combination of graphs. But it's hard. OK. So that's the graph complex, part 1. Not equal. I'm interested in finding non-zero homology classes. This is non-zero as a homology class. So the claim, which is non-trivial, is that it's not the image of the boundary. Is that clear? Yeah. If it's covered by triangles, yes. Oh, sorry, no. OK, so there's 2 things, one of which is an observation, the other of which is hard. If a graph is covered by triangles, then its differential is 0. That means it represents a homology class. But whether it's non-zero in homology or not is hard. Being non-zero in homology means you're not in the thing you quotiented by, the image of the differential.
But you did that by top degree in the first example.
That's right. In the first example, the graph theoretic proof is easy. But here, in general, wheels have vertices of have one vertex of valence greater than 3. So they're no longer in top degree. Yeah. Okay. So that's part 1 of the talk. Part 2. Is going to be a combinatorial topological construction that will furnish a new connection that we discovered between the graph complex here and moduli spaces. But this construction is sort of, in my opinion, purely combinatorial, and I would love to get more people involved in looking at these data structures. Part 2 is about a construction that we call a symmetric delta complex. That's the terminology and the setup that we use in our paper, though these ideas have been around, in particular in work of Berkovich on polysimplicial sets and earlier. The rough idea is this is some kind of data structure that encodes not just simplicial complexes, which are obtained from simplices by gluing along faces, but spaces that are obtained from quotients of simplices by permutations of their vertices by gluing. So the building blocks here are not just simplices, but quotients of simplices by automorphisms. C is me, G is Soren, and P is Sam. Yeah. Yes, that's right. So this formalism you find in our paper, but the ideas certainly have been around for longer. So let me introduce this category by recalling the notion of a delta complex in the sense perhaps you read in like the textbook of Hatcher, for instance. In other parts of the literature, these are called semi-simplicial sets. They're closely related to the notion of simplicial sets in topology. So let's recall a delta complex. So again, let me draw some cartoons. A delta complex is obtained by gluing, some simplices in a way that respects the orientation on the simplex, the respective simplices, whereas symmetric delta complexes will be some way of gluing together pieces of simplices mod some automorphisms. Okay, so what is a delta complex? Well, for me, it is, for each number p, it's the data of a set xp. This set I will think of as a set of names of p-dimensional simplices. And some gluing data. For each number q less than or equal to p, a set map from xp, for each q less than or equal to p, and an injection from 0 through q to 0 through p, which is order preserving. I'm going to continue this split board over here. An order preserving injection. The specification of a set map corresponding, maybe I'll call my injection J, then I have a set map function from xp to xq. My intuition works best when q is p minus 1, in which case an order-preserving injection is nothing but the specification of a single number, say I, that you miss. And then this set map tells you the ith facet. It names for you the ith facet of a given p-simplex. Moreover, this data had better be compatible with compositions. In other words, it all assembles into a functor. So a delta complex is a functor from the category that I'll write OI contravariantly to the category set. Here, OI is a category that we've essentially seen on the board. It's objects are sets 0 through p, and its morphisms are order-preserving injections. I need more room. So at the moment, this may not look anything like what you saw in Hatcher's textbook because there are no spaces involved. I prefer to do the combinatorics separately and then put the spaces in. And the way we do that is by geometric realization of this combinatorial data. So to be formal, I'll continue temporarily up here. There's a functor. I'll write it with bars. It eats in a delta complex, and it spits out a topological space. And I don't wish to write the full formula, but you can imagine how this works. If you're given a delta complex, you pull out a physical p-simplex for every element of xp, overall p's, and then you glue with face maps according to the data of these set maps xp to xq. OK, so a symmetric delta complex, let me start the definition in parallel here. A symmetric delta complex is nothing but by definition, it's a functor from fi op to set, where fi is the category made famous in rep stability, though that's sort of accidentally related here. The objects, again, are finite sets, 0 through p, for all integers p. And the morphisms are any injections, order-preserving or not, doesn't matter. That's a symmetric delta complex. It's a functor from fi, contravariant to set. So it's sort of similar data for each, let's spell it out, for each p. We have a set, xp, which I regard as a set of names of p simplices. And for q less than or equal to p, and an injection, which may or may not be order-preserving, crucially. From 0 through q to 0 through p, we have a set map xp to xq, just as before. And there's a notion of geometric realization, which has the same formula as that which I did not write down for the geometric realization functor on symmetric delta complexes. Yes?
Just a quick clarifying
Yeah.
question. Can you say again what is the category OI and what is the category FI?
Yes. I'll tell you the objects and the morphisms. The objects of OI are finite sets 0 through p for all integers p. The morphisms are order-preserving injections. That's the O. Whereas here, the morphisms are arbitrary injections. This distinction, thank you. This distinction is important because, for example, if q equals p, we pick up all elements of the symmetric group sp plus 1 among the injective maps. And they're exactly the injective maps. So So morally, and in fact, in reality, that is the reason why when you make a geometric realization of a symmetric delta complex, again, whose formula I didn't write down, it can involve gluings of simplices, not just to positive codimension faces, but to themselves via permutation of vertices. So I'll give you an example. Again, suppressing the actual formula for geometric realization, but just to get the intuition down. So the intuition is, let's consider the delta complex case, just to warm up. So here, consider an interval. It has two vertices, and one edge is oriented. The edge is oriented. So here, this interval has one simplex, and it has two zero simplices. And for each of the two order-preserving injections from a one-element to a two-element set, there are set maps. One is the head map, and the other is the tail map. A symmetric delta complex allows you to model what I'll call h, the half interval. And I'll draw it like this. It has one vertex and one edge. H1 is the one element set E, and H0 is the one element set V. So the head of E is V, and the tail of E is also V. And crucially, like most importantly for this example, there is now a new morphism in the category Fi that was not present in OI. It's exactly the non-trivial permutation of these two elements. And associated to this morphism, let's call it J, you're obligated to give a set map from H1 to H1, which of course there's only one thing it could be since H1 has one element. But this combinatorial, like this data inside the symmetric delta complex says that when you go to geometrically realize it, you end up gluing the edge E head to tail, tail to head with itself. And that's why the geometric realization looks like this. So as an exercise/example, let's do half a triangle, and we can compare notes. So another example, this is now this is a right side of the board example of a symmetric delta complex. It's half a triangle. And I'll leave it as an exercise that this, as a symmetric delta complex, has two vertices, or two zero simplices, three edges, and three two simplices. So symmetric delta complexes are a convenient data structure to keep track of the combinatorics of spaces that are glued from simplices modulo automorphisms. A proposition that we prove with Galatius and Payne is the following. So for each P, so this proposition is a cellular homology theory over the rationals for symmetric delta complexes. Let me let for each P, C sub P, so given a symmetric delta complex, for each P, let me define the Pth cellular chain group, say with rational coefficients, to be the tensor of the sign representation as a Q SP plus 1 module with the permutation representation on the P simplices. This is a definition. Let's spell this out. This is the vector space freely generated by the set of P simplices, modulo the relation that a P simplex X is identified with sigma X up to sign. This is for all X, a P simplex, and sigma, an element of S sub P plus 1. And I hope it's OK that I'm passing to symmetric groups. Again, the point here is that in the category Fi, you have all bijections of a P plus 1 element set. Therefore, the symmetric group SP plus 1 permutes the P simplices of a symmetric delta complex X. So spelled out, this is what the P chain group is of a symmetric delta complex. And then the actual proposition, which I haven't stated yet, is as follows. It's, well, first of all, that there is a differential which I will not write out. It's the usual alternating sum of dropping one element in turn. And this differential makes these P chain groups into a chain complex. And the theory, or the proposition, is that this chain complex is quasi-isomorphic to the usual singular chain complex of the geometric realization of X. I'll write X bar to mean the actual space obtained from geometrically realizing the symmetric delta complex. Recall what quasi-isomorphism means. It means that you have a map of chain complexes inducing isomorphisms of homology. In other words, if you're interested in computing the rational homology of a symmetric delta complex, then you can use this combinatorial cellular chain complex to do so. That's the proposition. And the proof, which I will not give, is actually quite similar to the standard proof, say in Hatcher, of the correctness of the cellular homology theory for delta complexes or CW complexes. You filter by the number p and consider p skeleton. It's a standard proof. Before going on from part 2, let me just make one passing remark, which is that given a p simplex X, it is 0 in this chain complex, in this chain group, if and only if its automorphism group is alternating. So it's as a subgroup of SP plus 1, it's contained in the index 2 alternating subgroup. Is it clear what I mean by the automorphism group? There is a subgroup of SP plus 1 that actually fixes X. So for example, the half interval has a 1 simplex that is not alternating because it has a transposition that fixes it. Yes?
Did you say what the absolute value map is for the symmetric delta complex? It's just what's gluing?
Yeah. So I explicitly didn't spell it out. It's the gluing you're thinking of.
Okay, great.
Yeah. So you take, for every for every name of a p simplex, you pull out from your workshop an actual physical p simplex, and then you glue according to the vertex-to-vertex identifications given by the maps J upper star, which are somewhere. But those J upper stars can be non-trivial permutations, thus simplices can be glued to themselves non-trivially. Yeah, yes?
Can I jump back to the board that you didn't erase about the wheels?
Yeah.
So you have this non-Bernoulli, but you say there's a relations among them or the dimension of that space, and are you that node? Are you coming back to that?
There are huge mysteries here. This GC is full of deep mysteries. So there are structures I haven't told you about. GC is a co-Lie algebra. It's dual to a Lie algebra. And that's true for all graph complexes associated to arbitrary cyclic operads. And therefore, the homology is a co-Lie algebra. And a remarkable theorem of Willwacher identifies H0 with the dual of the so-called Grothendieck-Teichmuller Lie algebra. The Lie algebra is associated to the Grothendieck-Teichmuller group as introduced by Grothendieck to study the absolute Galois group of Q. These wheel classes are also related to, in a way that takes explanation, they're related to the stable homology of general linear groups, GL and Z, which some of you may recall, or whatever, that it's generated in degrees 5, 9, 13, and so forth. So yeah, there's a lot here. And as a combinatorialist, I had to come to terms with the fact that these combinatorial definitions yield objects that don't necessarily yield two combinatorial proofs. Yeah. They correspond to, so they're dual to the Soulé classes sigma 3, sigma 5, and so on. Yeah. Okay. So that was part 2. And you can already see, perhaps, a potential connection from part 1 via part 2 to something. And I wish to tell you about that something in a short part 3 of the talk. Yes?
Sorry, could you say again how this has 2 vertices, 3 edges?
Yeah, okay, exercise. You can see the 2 vertices. You can see 3 edges. So this is one of them, much like the half interval. And here are 2 of them. There are 2 one simplices here. They're glued head to tail, tail to head. And here, I think if I counted right, there are 3 barycentric cells here. So there should be 3 triangles glued, if I got it right. Yes. So now for part 3 of the talk, which is a moduli space in tropical geometry. So I will introduce a space for each genus G, for each number G, at least 2, a space that will denote delta sub G. It is a moduli space for tropical curves of genus G. And I will explain what I mean by each of these terms. First, a moduli space. A moduli space is a fancy version of the concept of a parameter space. A moduli space for some class of geometric objects of interest is some space whose points are in bijection with the isomorphism classes of the objects you're trying to parameterize. So it's a fancy version of a parameter space, satisfying some universality properties that will be not part of this talk. What is a tropical curve, and what does it mean to have genus G? I will define this precisely for you. So for me, what is tropical geometry? There are many different related precise instantiations of tropical ideas, but roughly speaking, it is a degeneration technique in algebraic geometry in which an algebraic variety, some space locally defined by polynomials, is replaced perhaps through some limiting process or some passing to the boundary, by a purely combinatorial object, which one hopes retains some, if not all, of the data of the algebraic variety that you started with. There are lots of different sort of related ways to make this precise. And so at this moment, I'll just say that for me, a tropical curve, which I'll define next, is the analog in tropical geometry of an algebraic curve. In other words, a Riemann surface. So let's now make this precise. A tropical curve is a triple, G, W, L. Here, G is a graph connected as usual, multigraph as usual. W is an arbitrary function from the vertices to the non-negative integers. And L is a metric, so it's a formal assignment. It's a function from the edges to the positive reals. Let me make a normalization condition, which is not super important, which is that the sum of the edge lengths will just stipulate to be 1, so it's a total edge length 1 metric graph. And continuing the definition, this data is required to satisfy that the graph that'll denote G upper W, which is the graph obtained from G by sticking on W of V loops based out of vertex V. Has minimum valence 3. So every vertex has at least 3 outgoing half edges. This is a condition that comes from the Deligne-Mumford stability condition on algebraic curves. But combinatorially, I view it as roughly saying that vertices have to be topologically non-trivial. You imagine this weight function W, as recording the number of ghost loops at your vertex, which are restored in the graph G upper W. And finally, we define the genus. Sorry for the board work, I'll define it down here. The genus is the first Betti number of the graph G upper W. So that is a full, precise definition of a tropical curve. So now we wish to make a moduli space of tropical curves of fixed genus G. For each fixed G, there are, in fact, finitely many combinatorial types, G comma W, finitely many just purely combinatorial data, omitting the length, up to isomorphism. And for completeness, I'll give you the full picture when G equals 2. This is a picture I've drawn many times since graduate school. And you can check the various conditions as an exercise. So there's 6 combinatorial types. There's a poset structure. It's actually a little better than that. There's a symmetric delta complex structure, but just at this level, there's a poset structure. Here's the Hasse diagram. So now, we want to cook up a space that parametrizes up to isomorphism ways to put lengths on these edges. Lengths, positive real length summing to 1. So we could start by working one picture at a time. For example, the upper left picture, the theta graph. To parameterize isomorphism classes of metric theta graphs, you might want to take an open simplex parametrizing triples A, B, and C, lengths summing to 1. But note that ABC and BAC and CAB and so forth all connote the same metric graph up to isomorphism. So better, actually, for the purpose of parametrizing only objects up to isomorphism. Sorry, I should have written the whole point, which is that as a set, delta G parametrizes tropical curves of genus G up to isomorphism. Okay, so now let's start again.
I don't usually think tropical G has boundaries or not.
I don't know what that means.
If I'm actually
Yeah.
looking at curves, do I have my curves have boundaries or mark points?
No, at the moment, yes. Okay, so here is one of the 6 barycentric cells, for example, parametrizing triples A, B, C, such that maybe A is at most B is at most C. That parametrizes metric theta graphs up to isomorphism. And there's one such space for each of these 6 pictures. For example, for the top right, which is the barbell graph, you have half a simplex parametrizing A, comma, B, comma, C up to the relation ABC and CBA are identified. And you can do the same for the lower dimensional simplices corresponding to graphs with fewer edges. And though I haven't given you the definition of the topology, you can now imagine it, and I'm trying to illustrate it for you in the case G equals 2. So the topology is obtained by identifying these boundaries of cells which correspond to the notion when an edge length goes to 0, with the resulting graph that's obtained when the edge length actually goes to 0 is contracted. And in this way, you get a space that is made of simplices modulo symmetries. So this is an actual picture of delta 2, though I've suppressed the official definition of the topology on this space. So I'll end now by making official what you can see in this example, which is that delta G, this tropical moduli space, has the structure of a symmetric delta complex. And then end with a theorem, same authors, which is that we found that the homology of Kontsevich graph complex, I'm going to suppress degrees because the degree shifts are just distractions at this point. The homology of the graph complex is identified with the rational homology, the reduced rational homology of delta G. And the reason we care about delta G and its reduced rational homology is that it admits a canonical surge action with degree shifts suppressed from the rational cohomology of this famous variety, MG, the moduli space of genus G curves. This talk has been about this isomorphism, and I haven't talked much about this canonical surjection, which essentially follows from the work of Delignon and mixed Hodge structures, except that this physical instantiation as a combinatorial moduli space hadn't really been, explored in the 70s when the theory of mixed Hodge structures was developed. The identification of this space delta G with the boundary complex of the important Deligne-Mumford compactification of MG only came later in the work of Abramovich-Caparaso-Payne. This is the part that I'm not talking about, but this is the part that I am talking about in this talk. There are two things to say about this isomorphism, A and B. So A is, on the right-hand side, we have something that involved vertex weights, but on the left-hand side, we didn't. That is rectified by a sub-theorem that says that the sublocus of delta G, parametrizing tropical curves with positive vertex weights, is contractible, with at least one positive vertex weight. This is contractible. So for purposes of homology, we can throw it out. And then B is that we find, and you can probably see a sort of shadow of this on the board, that GC is quasi-isomorphic to, I have to take all genera at once, because the left-hand side takes all genera at once. So this GC is quasi-isomorphic to the cellular chain complex over all G of delta G as a symmetric delta complex. Putting facts A and B together yields this proof. And finally, remarkable theorems about the homology of graph complexes that were coming from the world of deformations of EN operads and so on, produced for us unexpected cohomology classes of MG, which actually disproved a conjecture of Kontsevich from those initial papers that I described. Okay, thank you very much.
So we had many questions during the talk, but do we have any further questions for Melody?
Can you explain again how to get, in this example, here 0, 1,
Okay, yes, so in the category Fi as compared to OI, there is a morphism that takes 0 to 1 and 1 to 0. And associated to that set map, we're obligated, according to the functor, functors send morphism to morphism. So the functor has to spit out a set map from the set of names of one simplices to the set of names of one simplices.
Sorry, where does 0 come from? Like, what is 0 and what is 1?
Those are numbers. Yes. So 0, 1 is an example of an object in the category Fi. Yeah. So that object I think of as it's an object in an indexing category. And the data of the symmetric delta complex gives a set of names of P simplices to the index set 0 through P. Thanks. Yeah.
Feel free.
In the back. Yeah, whatever.
I actually have two questions. So what was the original motivation for Kontsevich to define this, and what's known about the homology of positive degrees?
Yeah, thanks. The original motivation was the study of a certain stable homology of an infinite dimensional Lie algebra that arises in some non-commutative geometry setting, Poisson algebras. That stable homology has a Hopf algebra structure, as is typical for stable homologies. And if you look at the primitive part, then modulo a known primitive part, which is the primitives of the symplectic group Lie algebra, it's equal, as Kontsevich shows, to the total graph homology. He actually defines 3 different graph complexes, or 6 if you count variations in orientation, associated to commutative, associative, and Lie. Commutative is what we study. Associative is related in a different way to moduli spaces of curves. And that's the conjecture of his that we disprove, strangely. And Lie is related to outer automorphisms of the free group FG. As for what's known about graph homology in positive degrees, it's a huge mystery. There are asymptotic calculations by Berinsky, I think very recently, and computer calculations by Bar-Natan McKay and by Wilwacher. But there's a lot more to be done. For example, it's conjectural that H1 is 0, but it's not known.
Okay, I think we'll have to stop the questions there, but let's thank Melody again.